My part will be covering introduction, voltage quality aspects, and cause of poor power quality. Starting from introductory topic, I will explain what, in my view, why voltage quality is important, and I will try to also explain difference between reliability, sometimes referred to as continuity of supply, and voltage quality. So what are the reasons to address power quality? First of all, it is market transformation and liberalization and cost-saving issues, which not must but may deteriorate quality. That's why energy regulators have a role to guard this quality. Then we have risk to continuity of supply due to contingency issues, due to large number of generators now, and all the level of sophistication of today's electrical network, and also, things like severe weather conditions. Then we've got the compatibility aspects, which are also the reason to address power quality, as equipment has its emissions, but also immunity, and voltage quality and power quality in general may affect these aspects. Finally, last but not least, is voltage quality, which is actually today's subject. Today, loads are largely dominated by nonlinear elements, which influence supply, but are also sensitive to voltage quality problems. The issue here is sometimes addressed by a concept of so-called responsibility sharing, where every part takes responsibility for securing its compatibility issue. Now, what kind of quality of supply components we usually distinguish? So, first of all, it's a continuity of supply, which is a mostly engineering issue related to DSO operation, and it's partially regulated or rather advanced regulated, particularly in some countries. In some countries, we've got all this aspect completely under regulation. Then we've got voltage quality, which well, here it's not regulated. It's not regulated in principle in the strictest sense, but Walter in the second part of the session will address regulation of voltage quality. And then we've got a commercial quality, which is in most of the countries well regulated. Let me move to the next slide. So now let's go into detail into these domains. So commercial quality, continuity of supply, and voltage quality. I think you can read faster than I can speak. So on the right hand part, you've got different functions which are written into these three sectors, and some of them are related to electricity seller, and some of them are related to technical issues, either in generation, transmission, or distribution. Regulation of quality, how we can regulate the quality. So prerequisite is information tool. So set reliable measurement rules for quality factors, publish quality levels. Then we've got next one, which is a sort of incentive quality regulation, which is protect well-served customers by a set of standards or determination of individual compensation for standards. Then we've got promotion of quality improvement, when we set and maintain, develop quality standards, and link quality to revenues, because not necessarily every user has to have absolutely maximum level of quality. Then we've got the market mechanism, which is also giving a choice to customer. It's it's a matter of competition. It's giving customers a choice, as he may have different preferences according to willingness to accept or willingness to pay mechanisms. Now, what are the differences between continuity of supply and voltage quality? So first of all, when looking at customer side, for continuity of supply, customer is affected by every interruption. While for voltage quality, customer is not affected until certain voltage quality level. So we have certain immunity somehow written in the concept of immunity to voltage quality. For continuity of supply, lack of reliability means cost for all customers, while for voltage quality, different effects are for different customers. For continuity of supply, power interruptions are mainly caused in the network, while for voltage quality, largely depends on, or is largely influenced by other customers. Now we've got a chart which is illustrating things which I described on the previous slide. So for reliability cost curves for interruptions, we've got let's say a 0-hour cost. So once the interruption started, we've got already a certain level of cost, and then we've got different shapes of cost curves. While for power quality, we've got immunity, then the costs start to rise, and usually the shape, of course, is similar to this of reliability, as usually the product of power quality of voltage quality problem is outage. So it's basically the same as for reliability. In technical terms, when we compare the interruption to technically to voltage dip, they are very similar, although they are caused by completely different things. So for the interruptions, it is basically permanent fault, longer or shorter. Why for voltage dips, it's usually switching operation, switching of large loads, and basically the difference between both is that in voltage dip we still have some residual voltage. It can be as low as few percent, but it still exists. Why for interruption we've got zero voltage. That's why some people used to refer to zero voltage events when referring to interruptions. Now I would like to present some slides about European standard EN 5160, which is defining conditions which are to be met in public electricity networks. So first of all, we've got different parties which are actors in voltage quality arena. So first of all, this is a network operator which has a task to operate the supply with suitable parameters. Then we got network user, which should limit the possible disturbances introduced into the network, and also bring some immunity to equipment for situations when the voltage, when the electricity supplier cannot longer help. And then we've got the third party, which is manufacturer of equipment, which should minimize the level of injected disturbances and, of course, immunize equipment. Now, it's a chart presenting most of the disturbances covered by EN 5160. So we've got from the left nominal voltage, then we've got supply voltage variations, then we've got rapid voltage changes, then we've got flicker severity, then we have voltage dip, and then we've got short interruption and long interruption, which are not voltage quality events. And then we've got over voltage with network frequency, and then we've got spikes, we've got transients over voltages. This, what is not represented by this figure, but is included in 5160, is of course unbalance. Well, what are the terms of EN 5160? This presentation, I think, will be available after today, so I will not read in detail every term, but in general, it defines parties contributing to voltage quality. Then it gives definitions, different voltage definitions, which are not very far, from each other, but there are some small differences. Then places like a point of common coupling where loads are connected, and frequency. So all these terms are defined in 5160. Then we've got definition of what is normal operating condition, and then EN 5160 divides voltage into three voltage levels. One is high voltage, which is between 36 kV and 150 kV. We don't have extra high voltage because customers are not connected to extra high voltage terminals to have the high voltage level. We've got medium voltage between 1 kilovolt and 36 kilovolt, and low voltage with RMS value below 1 kilovolt. In some countries, there is a provision that in some countries some borders, some limits, can be slightly different. Normal operating condition is a condition for electricity network where load and generation demands are met, system switching operations are made, and faults are cleared by automatic protection systems in the absence of exceptional circumstances. And now we got these exceptions, which is temporary supply and not permanent and not stable, but temporary supply arrangement. In the case of non-compliance of network user installation or equipment with relevant standards, and exceptional situations, such as exceptional weather, third-party interference, acts of public authorities, force majeure, and so on. It's I think, a very good chart explaining what means compatibility and and why we got this philosophy of 95 percentile in European net in 5160. So actually, on x-axis we got let's say this axis, we got level of disturbance. It can be whatever. It can be level of harmonics. It can be flicker severity. It can be even voltage value. And on this axis, on y-axis, we've got probability density, and then we have distribution of let's say public supply of technical conditions of electricity supply provided by network operator, and then we have equipment immunity. So in general, equipment is immune to with certain margin, which is called this compatibility margin, but some percentage, some small part of immunity of equipment may not be may be still sensitive to, let's say, worst part of supply conditions from public network. And of course, the network operator duty is to move this left probability distribution most to the left, and which of course cost capital cost to supply network, while the manufacturer of equipment should move this right curve, immunity curve, most to the right, just to have this percentage when you have situation when immunity and supply cross each other, to the minimum. And this, let's say, remaining percentage, for which network operator cannot or should not take the whole responsibility is somehow addressed by this percentile, which we have present in EN 5160. I think it's a good analogy. It's a Viaduct analogy when we've got a track and equipment track manufacturer should make some provision, some margin, from the compatibility level, which is here, and for planning level, the constructor of a viaduct should make provision, for example, some rough pavement, or snow or whatever. So both sides should do efforts, to get rid, of the other player and increase the margin between both. Now coming back to EN 5160. So this table represents frequency and supply voltage. So we've got this percentile issue shown here. So for example, for frequency, for plus minus 1%, we've got 99.5 percentile for synchronous connection and 95% for asynchronous connection, and 100% for plus 4 minus 6% of frequency, and also 100% for non-synchronous systems. And this is for synchronous system for supply voltage. So this is plus minus 10% for 95% of 10 minutes root mean square value. While for plus 10 and minus 15, 100% of the time, this condition of plus 10, minus 15 should be fulfilled. And this, and we've got here the conditions for asynchronous network. Now, it is the standard also addresses flicker, and this is example of how 95 percentile can be used. I mean, if 95 percentile of long-term severity of flicker is below below 1, it means that we have compliance to standard. Let me speed up a little bit. So now we have how we address voltage dips. So this is a classification of voltage dips proposed by EN 5160. Well, basically, this classification. So for collecting, I think now we've got much more results about what we can expect from today's power quality network. And to speak the same language, this classification is made. And we've got basically three classes of equipment. Class 1, which always has to be supplied through adequate conditioner through UPS or so, which has almost no immunity. Then we've got class 2 equipment, which is immune basically to voltage dips, which are here, which is cell A1, A2, B1, and B2. And then we've got equipment class 3, which is most of types, of equipment met in industry, which is A1 to C1, then B2, A2, and then A3 and A4. Next slide is about in our curve showing compatibility, and we've got 3 types, let's say, of events. We've got immunity limit for voltages, for voltage dips and supply interruptions, and to range of tolerance. And we've got type 3, which is from 2 seconds up of very short voltage variation. Then we've got mostly voltage dips and sags. with a duration between I think half cycle to 2 seconds, and we've got, let's say, temporary spikes, or very short term but very high magnitude events which are type 1. I will speed up. Now we've got the same, during each period of 1 week, 95% of each of 10 minutes mean RMS values. So we've got positive and then negative sequence harmonics. We've got zero sequence harmonics, and we've got even harmonics levels in 5160. Then we've got unbalance, and for 95% of 10 minutes RMS, the ratio of negative to positive sequence should be up to 2%. In some exceptional reasons, it should be up to 3%. Next one is about measurement. It is not particularly the part of PE and 5160, but it's I think worthwhile to know. That we've got the class A equipment because it verifies compliance to EN 5160. And it is class A, which has sampling of 0.2 seconds, then aggregation of 3 seconds, 10 minutes, 2 hours. So it is basically the equipment which should be used for all contractual issues. Then we've got class S, which has the same averaging principle, but should not be used, for contractual purposes. And then we've got class B, which is steadily withdrawn, and it's rather obsolete type of equipment. Then the last part of my presentation is about cost of power quality. In 2005, we performed a power quality survey in which we investigated, examined like 60 sites by in-depth interviews. And what we found that for industry, the most disturbing are dips and short interruptions. And industry is the hardest hit. The services sector, which is everything except industry, is experiencing power quality problems much less. And then the balance of problems is more even, and dips and short interruptions or surges and transients do not dominate as much as for industry. So the total power quality cost in Europe is exceeding 150 billion. As I said, industry is the hardest thing, and what we found is that for most sensitive industrial sectors representing 3.5 trillion turnover, which is 20% of EU 25 overall turnover, for these entities, PQ cost amounts about 4% of their turnover. For services, the impact is much larger. It's much smaller. Then we've got similar but earlier example from US when EPRI investigated cost of they called zero sequence events, but also power quality problems, and they found they made study based on digital economy, continuous processes, manufacturing, fabrication of essential services, and they extrapolated to the whole economy, and the cost may be between 119 to 188 billion US dollars, and in EPRI findings, power outage related to zero voltage events is dominating. What they found, is that this is a cost of 1 second recloser, so it is the second after auto recloser operation, a second event. Then we've got 3-minute interruption and 1-hour interruption. And what we found is that even if recloser is time of duration of a second, event is the same as the first one. And the second one, we've got much larger cost of equipment damage. So equipment is somehow immune to first event, but it's not that much immune to the second event coming after operation of the closer. Then general finding is that, of course, we have no proportion. I mean, the number matters, not the duration matters. So 1 second event is even, this one is even more severe than 3-minute interruption, and it's only 3 times less costly than 1 hour interruption. Now, the next finding is an Italian study on how much voltage dips can cost, and you've got the value for mediana here and mean. I think mediana is probably characterizing the performance better than mean, because mean there is a big differences between companies, and probably mediana is better measure to compare severity of voltage dips. Severity to costs, and this is about 10 euro per kilowatt of lost load, and excluding zero direct cost sites, then the value doubles. Next one is about sensitivity of different sectors to voltage dips, and definitely continuous manufacturing, like semiconductor industry, is the most sensitive. The next example, I think I had also another one, but these are cases quoted by Jovita Milanovic and Professor Jenkins from University of Manchester, and you can read from examples how was the loss in these different events. Finally, I would like to say a few words about why is it worthwhile to investigate the cost of power quality. First of all, it's a general awareness issue. Then we've had the issue that statistics may not be helpful, as there are very large differences between companies. Every company has different has different loads, has different sensitivity to loads, has different different disturbances. So the only way to find out how the cost is to make a survey themselves. Yes? Okay, I'm nearly finished. Then the next issue is to know about cost, as we may expect compensation from the supplier if the power was supplied not properly, or is it also worth to know how much we can pay more for extra service? Then we've got also a specific awareness issue that it may justify the effort to improve power quality, and finally it is used by regulators to improve regulation of voltage quality. The last things, is invitation to Leonardo Energy. So we've got microsite of Leonardo Energy of power quality. Sorry, is somebody trying to tell me? Okay. And so I invite everybody to our Leonardo Energy power quality micro. And finally, I'd like to invite you to Leonardo Academy. You've got a URL given here. I'm a manager in this Leonardo Academy, and we've got a comprehensive course on power quality, which is composed of 10 topics, and we've got also short topics extracted from this large course, and many other interesting things in our Leonardo Energy Academy. Now I would like to finish at this point, and to pass flow to Walter. Thank you.
Roman, thank you very much for your presentation. My name is Walter Hulshorst. I'm within DNVGL, and I want to tell tell you something a little bit more about the mitigation measures of power quality, guidelines for voltage quality regulation, and then finally our conclusions. As you might have seen, Roman already discussed the voltage quality aspects which we have, and also the cost of poor voltage quality, and I would like to focus on the last 3 parts of this presentation. Mitigation measures. Well, as Roman already told us, you might have seen that a lot of industries which might have some problems with cost related to poor power quality aspects, and that justifies also mitigation technology to prevent that you might have a power quality problem. In general, there are 4 solution areas on which you can think, and basically I think most of you might know this kind of picture. It's a pretty old one, but it's still usable today. There are 4 locations mentioned in this picture where you can identify or mitigate your power quality. Number 1 is specify your equipment or the proper methodology so that you don't have the power quality issues anymore with your equipment. Number 2 is try to have some control protection. Could be a kind of small backup in your equipment. You can think about a laptop versus a desktop computer. If you have a voltage dips, for instance, within desktop, it will immediately shut down. If you have a small battery in it, like a laptop has, you have some prevention measures. Number 3 is an overall protection on your site, on an industry site, for instance. And number 4 is a utility solution. And note that the further you go from 1 to number 4, the cost will also be higher for the mitigation measures. And it depends also, the mitigation method depends also on some aspects. Before you make a solution, if you want to have number 1 or number 4, please think about the issues mentioned over here. And they are very strict on the purpose when you want to have your mitigation measure. Next to the technical mitigation measures, there is also an opportunity nowadays more that there are some DNOs, distribution network operators, which provide contracts for customers which must have a high power quality performance. You can have a lot of technologies, and you can also have a contract with your DNO. They are so-called premium power quality contracts. So the DNO is giving you more power quality than you normally could expect because you need more power quality. It's basically a contract which you have. Also, a new aspect is labeling. It's more a kind of, that in some countries where you have a minimum standard for voltage quality, and you also need to know that you have some customers which are willing to have a higher quality. You can have a kind of so-called labeling effect. And labeling basically is when you have a normal level which is acceptable, it's called a C. If you have a very poor power quality level, it's called an F, and if you have a very high quality, it's called an AA. Basically, this is a methodology which is also used. Most of you might know in European, if you have an energy efficiency program, you know, if you have a device with a very high energy consumption, it's called in this case an F, and if you have a very nice one with less energy consumption, it's called an A, or even today an A plus or A triple plus I've seen also. Basically, you can also identify it with your quality aspects, power quality aspects in a grid. In the Netherlands, there is one DNO who tried to do it, but to tell you the truth, it's very cost effective if you want to do it this way, if you want to do it for all kind of power quality aspects, because you really have to measure almost on every location what it will be, an A classification, a B or a C. And then you can also, if you have if you show these parameters outside your company, your DNO, you may have some customers asking, hey, why do I have a C quality, another one has a B or an A quality, I also want an A quality. Then you have to deal with that, and who is going to pay for it. Also some guidelines for power quality regulation, and mainly there are 3 which I would like to discuss with you. When you set up a framework for voltage quality regulation, there are some issues that you need to consider first. The first one is mentioned over here. It's develop a good understanding of what voltage quality is and how it can be measured. You might know that voltage quality, well, there are different aspects of voltage quality. What kind of aspects are you going to measure and how are you going to measure it? That's also very interesting to know, and I'll discuss it later on with you. After you know that you can measure it, what will be your objective in case you want to regulate it? And Roman already mentioned that you can use it only for information only. You can also try to have a regulation to protect your worst served customers. Also, perhaps to have a better improvement of your power quality. All those aspects should be clearly defined before you start regulating on voltage quality. And then, after all, once you have done it, also try to make a mechanism on which you can also control your power quality aspects within the DNOs. Measuring of the voltage quality. There are some issues which we really have to identify. Measuring voltage quality, well, of course, when you want to regulate on voltage quality, you need to measure your voltage quality upfront. You need to identify what are you going to measure. Nowadays, you will see that in some countries they already started with smart metering, and so a lot of low voltage customers already have a kind of measuring smart meter within his home. Perhaps you can also try to use those smart meters for your quality, your voltage quality. But do know that you perhaps the voltage quality which you want to measure, if you for instance want to measure also the harmonics, it might be that the measurement to the smart grid measurement smart metering in the houses is not sufficient to measure all those aspects. So think about that also, what are you going to do, and also where you are going to measure. And please know that, well, measuring is very important. If you don't measure the right data or you get wrong data as input, then you will also get wrong outcome of it, of course, which the regulator has to find out with the information which he can hit you with wrong data. Also, within the regulation, there is a council of European energy regulators, and there was also they did an investigation, I think about 1 year ago, about voltage quality monitoring. They did it together with the energy community on the regulators board, and they had some advisements before you start with voltage quality monitoring, which is needed before you can start with regulating. And their conclusion was basically that voltage quality monitoring is a very useful tool for regulation. Well, of course, if you don't monitor your voltage quality and you want to regulate the voltage quality, you need the monitoring. So that's a very an open eye, I would say. There is also a diversification of indices and methods to be avoided. There are some programs, and you can discuss about it, that there is some harmonization is needed between all the countries. Some countries already started with a voltage quality monitoring program, and they can differ between the countries. So if you have a European regulator or the community for council for European energy regulators, if you want to make sure that you compare similar power quality aspect and similar data, which is measured on a similar way, then you should try to harmonize it. Next step by step, voltage quality monitoring programs should be funded also through a network tariff. That's also very important because, well, you can set up as much meters as you want to, but someone has to pay for it. Is it the DNO or is it the regulator? And the regulator advises that you do it within your network tariffs. That makes sense according to my opinion, because the industry normally pays a higher price for the network tariffs than your householding does at home. It makes sense that they pay a little bit more also for voltage quality monitoring, as Roman already told us, they suffer more when the power quality is not good enough. And this is basically what the CEER concludes. And they also had a conclusion that the results of the monitoring should also be available. It's very important for them. Publication, well, it can be done either by the regulator or by the DNO himself, but it's part of the deal. Once you have a voltage quality monitoring system with the DNOs, publish also the data. And another aspect which is important is that you keep other applications in your mind in case you start with the voltage quality monitoring nowadays. Make sure that the voltage application you might have now can also be used in the next future for other aspects as well. I already gave you the example for a smart metering device at house. If you have such a metering at house and you want to use it for voltage quality monitoring and you can't measure the harmonics, well, then perhaps it doesn't make sense to use that kind of metering devices at this moment. So that's something you have to discuss about before you start with the monitoring. So those were the advices from the CEER report, which is published almost 1 year ago. The next step after you have done your monitoring is that you also have to define your objectives. Why are you going to regulate the voltage quality, and what will be the objective? Is it only for information only, or do you also want to promote the power quality, voltage quality, to improve the voltage quality? And I think most of you might know the figure I've shown here. On the horizontal axis you have the quality, and the higher the quality is, the more it will go to the right. On this axis, the vertical axis, you will see the cost of power quality, and basically you have two kind of costs. If you have a very low voltage quality, then you will see that the interruption cost, or the cost for poor power quality at the customer side will be very high. That's what Roman also discussed. If in the case the power quality is getting better and better, the cost will be less. But you have to invest into your grid to have those kind of values. So at a certain moment, the cost of the grid will be very high. And then the upmost optimal side is when those two together have the lowest cost. That's the social cost. And that could also be a parameter on which the regulator says, I want to be as close to this kind of cost for the regulation program. Also, another one is that you have the appropriate quality control. Once you have defined your objectives, how are you going to make sure as a regulator that you achieve those objectives? And there are basically also three methodology which you can use, which I would like to discuss with you. You can only do with performance monitoring. That's mainly the regulators only monitors the performance of the network company, and perhaps some information will be made available to the public. The next step is that you can also define as a regulator that there must be a minimum standard. In most cases it will be the EN 15160. That will be a minimum level for performance. In case your performance is lower, you will get a penalty as an DNO. And the next one is also an incentive scheme. And if you have, that's meaning that you have a relation, it's a kind of minimum level standards, but in case you are closer to the achieved value, you will get a financial reward, or sometimes if you don't have a value which you have achieved, you will still have a penalty. But there's a relation between the performance of your quality and also the financial outcome. More in detail, if you are looking for it, performance monitoring is very simple to implement, and it's mainly the first time when you want to do a regular scheme on voltage quality. It's very easy, and the only reporting that has been done so far is basically report what the outcome of your monitoring program is. That's up to the regulator, up to the DNO, whether he wants to decide to share the information or not. It's also, I would say, the weakest form of quality control, as it only provides some information about the power quality, and there is no incentives for the utility to have better quality. Also, in terms of data requirements, there's very limited data is needed, and then you can already share some information with the public. If you have the minimum standards methodology, then you will have a kind of minimum level. You have to define it. The regulator has to define it. And in case you don't meet the standard, the utility will be penalized financially or another way. In that case, the regulator aims at increasing the performance, but the minimum should be a guideline where the network operators has to fulfill it. The regulator set a quantitative target which the companies must achieve, and if they don't achieve it, well, they will get a penalty, of course, and the minimum standard, as already mentioned, is in most cases, it will be the European standard EN 5160, but if a regulator has another aspect, he can also deal with it. And in some countries, you will see that they are more strict on other parameters as well. Then we also have the incentive schemes that can be considered as an extended minimum standard. The utility pays penalty in case he doesn't meet a certain prescribed level, the minimum level, but on the other way around, if the performance is better than the minimum level, he can also get a reward from the regulator. Incentive schemes are very useful if you are aiming to have or maintain to have your existing level or to improve your performance, because if a DNO improves the power quality, he will get a reward for it. So he can invest more, etc., etc., etc. But to tell you the truth, it's a very difficult one to measure the costs for each customer. And also, what are you going to do when you have a lack of quality? Collection, you need high quality data before you can do an incentive scheme. Basically, my conclusion is my last sheet. As Roman already told you, there are some costs if you have poor power quality for some industries, but also some other ones do have costs, and so it makes sense in case those costs are not social accepted that you have a regulation scheme. And the objective of the regulation to be clearly defined by the regulator. It's his responsibility on that. Whether if he wants to regulate, then he should make an objective for it, because otherwise it doesn't make sense to have a regulation, of course. And the definition of the voltage quality, well, it depends a little bit. You can try to find a desired level. It could be a minimum level, but also it could be your socio-economic level which you want to have. And basically, once the regulator has set up it, then you can have three types of quality controls, how you can monitor it. The first one is performance monitoring, and the second one, the minimum standard, and the last one, the incentive scheme. And as I already told you before, there were also some minimum standards which regulators can choose. Basically, I think voltage quality regulation is possible. There are some countries already dealing with it. Note that there are some differences within the measuring of the monitoring, how to measure all the data within the different countries. So it's hard to say if you want to benchmark countries, if it is possible, please make sure that you exactly know what the differences are between the measurement methodologies between the countries. So I would like to thank you for listening to the presentation from me and Roman, and in case you have any questions, please feel free to ask.
Okay, thank you very much, Walter. Thank you very much, Roman, as well, for your presentations. So now I would invite our audience to submit your questions through the Q&A pod, which is on top in the middle of the screen. And well, we will go through the various presentations. Sorry, through the various questions. So, one moment.
In the meantime, Fernando, can you hear me? Yes. I noticed a discussion, between Stefan Fassbinder and Al Warner, about EN 5160. And indeed, I know Stefan's reservations, about the standard. But I would say this way, that of course, it's not perfect, as all said, and I agree, before 2008, we had the previous version of EN 5160, which by that time, was the only document trying to describe the conditions, in public networks, and it was much, much worse, So what we have in 5160 is that we address many more disturbances, in the previous version. We have also covered other voltage levels. And I must say, I faced discussion about this new EN 5160, and there were different opinions. That 95% it doesn't make sense, because it's like 2 weeks, if I remember well, in a year, or so. Even 99%, is a pretty long time, to allow, for the conditions not meeting compliance. But for example, for voltage, value, we've got this 100% time, so no allowance, for any percentile, for plus 10, minus 15% limit. And for example, I remember, that utilities were very much against, and they were giving arguments that it will cost them billions of euros, for example, to have compliance, for example, flicker severity, in 5160. So it's a compromise. So it's a big compromise, and utilities have a sound voice, and the compromise which was achieved, finally, I think is something good, Although, as I already said, it's not perfect.
Okay, thank you for this comment. Meanwhile, we have a question, so let me just forward. What is the more used regulation for transmission? Thank you.
I think I can answer that question. This is Walter speaking. As I told you, that there are 3 ones. So I think the most common one, in case you want to start with your power quality or voltage quality monitoring, and then you have performance monitoring, which is used in some countries. The next step, and I think most of them already use it, is the minimum standard methodology. So there is a kind of standard which is set up by the regulator, and saying, okay, you have to try to get the minimum standard, otherwise you will get a penalty. I think that's basically the most common one at this moment, the minimum standard.
Okay, good, thank you. We have another comment, so 1 moment please. Yes, so are the EN 5160 group in communication with both EPRI and IEEE power quality standards?
As far as I know, I don't think so. This is, I think, European standard, and it's basically covering Europe. And well, I think in the US, other countries, we got different than I think EN 5160 grid code. Although I think many parameters, they are similar to EN 5160. Although we have even in Europe, some more severe regulation, which is called beyond EN 5160. So, for example, in Norway, but also in some other countries, I think Hungary is also an example. Some countries do have more strict conditions, than specified in EN 5160.
Okay, thank you. Any additional comment, Walter, on this?
No.
Okay, thank you. Good, so we have another question. How far is going the application of this standard related to the timeline of deploying huge percentage of intermittent renewables that EU is pursuing by 2020?
It's exactly the issue, that indeed, renewables can bring some, how to say, increased level, of disturbances, particularly, but not only wind, but also PV, into the public network, and it's finally responsibility, of a network supplier of public utility to guard a network, from negative implications, of this technology. How can I answer this question, related to the timeline of developing huge? Well, I think there is nothing about intermittent, power, or deployment of renewables in the standard. However, conditions by themselves, they are somehow applicable, for or they should be. How to say, taking into account, when giving permits, for installing new renewables in the network. I'm not sure whether I answered this question, but I see the link, between both, and indeed. So the firstly, EN 5160 was response to efforts of different regulators, particularly CEER, that which publish, so-called benchmarking reports when they compared, different supply conditions in different European countries, and there was a workforce, which was trying to upgrade the old EN 5160 standard, and it addressed basically the increased number, of power distorting, loads. But of course, from generators' point of view, I think it is an issue, and maybe in next editions, in next versions, of EN 5160, this matter will be more particularly addressed. But frankly, I'm not participating, to development of 5160. I'm not in participating to this group.
Okay, good. So let me go to the next question. Yes. So, in Ireland, we see a lot of concern regarding the connection of a lot of large-scale wind farms onto the grid due to harmonic distortion. Do other countries in Europe have shared the same concern? Well, I think it's quite related to the previous question. If you, Roman or Walter, have an additional comment, otherwise we will switch to the next question.
Yeah, I think it's true. There are also other countries. This is Walter speaking. Sorry. There are also other countries with harmonic distortion issues due to the large-scale wind farms, and also a lot of studies are being done and still under progress. Because that's really an issue at this moment. If you have, especially as mentioned, the large-scale wind farms. I do know that in Germany, I'm not an expert from the German market, but I think there is certification is needed for each renewable before you, especially before you add it to the grid. There must be a kind of party which said, okay, well, this is certification, and also one of the aspects is the power quality issue related to that before you can connect it to the grid.
Okay, thank you. I think last question related to the interaction between power quality and renewables penetration. The permitting process is considering the standards as obligation from the renewable project developer. So is there any requirement to project developers to integrate this standard? Thank you.
Yeah. Depends a little bit on if you say, well, if you only focus on the EN 5160, there was also some other countries which have higher levels, and also the DNOs or TSO can have their own guidelines before you can access the grid. As I mentioned earlier, for question 4, for instance, in Germany, you will need a certification process before you can enter it, add it to the grid.
I agree. I think it's a grid code. It's something different than EN50. EN5160, has a name, of voltage conditions. I think, in electricity power networks. It's something like. So it refers, to voltage only, and it does not, I think, address particularly, the issues, of connecting of wind power, So.
Okay. I think this topic is quite popular. We have another comment. This is probably not really a question. So why are DNOs hesitant to use the voltage and the power factor control facilities in wind turbines to assist with regulation of the network? Why do they insist on paying to do it all themselves and then charge us for the equipment not needed? Do you have any comment on this comment? Thank you.
No, I'm not from a DNO, so I don't know. Sorry.
Okay, thank you.
Okay. I'm not sure, whether I understood, the question properly, but to use the voltage and power factor control facilities in wind turbines to assist the regulation. I'm also in trouble, answering this question,
I think it's rather a comment. So if the person having asked wants to punctualize a bit more, otherwise we will go for the next question. So let me just put it on the screen. One moment. So. What are the global best practices for a regulator in setting up voltage quality monitoring? We need more capacity building for institutions in the developing nations. At this point, maybe, Roman, we can invite our audience to join some of the power quality e-learning courses. So would you mind, together with explaining, typing in the introductions window the link to the relevant courses so we can offer this resource to our audience? Thank you. Thank you.
I will not type a link, but it's Leonardo Academy. I think it's the URL is in one of the slides, and if you select the category of power quality, then you get 10 comprehensive power quality courses, and then many other specific topics, which are extracted from these 10 power quality courses. And I think the most, on EN50, well, EN5160, it can be found in many courses, because it's cross. It's a standard, but that's saying about different disturbances. Why in power quality courses we've got a breakdown, of topics per disturbance basically. So first one is voltage dips, then harmonics, then voltage changes, then over voltages, etc., then the reliability issues, and so on. So EN5160 aspects of it, can be found in many courses. Well, about indeed, it's a big framework, of monitoring in Europe, indeed, and well, I think the number, of measuring instruments, in the network, even in high voltage, was increasing rapidly, some years ago, and I think it's more and more popular, and it's used for contractual reasons, but for compliance reasons, but I think experience, is really increasing, and for example, I think benchmarking report, which I mentioned, CEER benchmarking report, also tells, which parameters, at which accuracy, at which level are being corrected, in per country, So I'm sending you, to this CEER benchmarking report. If you go to CEER regulator site, you will find, you can download, these reports, and then you will have the whole panorama, of what is being done, in measurement.
Okay, thank you very much.
But maybe, Walter, you want to add something?
Sorry, Ron?
Maybe you want to add something about voltage quality monitoring.
No. If I look at the question, I think the starting point is starting with monitoring voltage quality, and the best practice. I agree with you. There is a lot of information, I think, on your website, and in case there is not, feel free to contact us directly. Our emails will be given or are given, I think.
Okay, good. Thank you. So a final comment, recommendation. All standards in this power voltage quality to be developed should consider the increasing penetration of renewable energy in the grids. So indeed, we all agree with this. Okay, so at this point I think there are no more remaining questions. So thank you very much for your presentations, Roman and Walter. Thank you very much to our audience for your interest and your interesting questions and comments. And we remain in touch for the upcoming sessions on the Clean Energy Regulatory Initiative webinar program. Meanwhile, I will give the floor to Walter and Roman to close the session today. Thank you.
Thank you, Fernando, and it was my pleasure, to talk to you, and I invite you, to the Leonardo Energy website and to our academy. As I said, power quality courses, but also other courses, sustainable energy, energy efficiency are available there. So see you there.
Roman, there's hardly anything to say anything more than you already said. Thank you very much for being with us with the presentation. It was very nice to present it to you. And I fully agree with the last question, I have to say, from Core. That's the only thing I would like to say. Yes, there is more standards are needed for the renewable project in the next future. Fully agree on that one. So that's my final word, I would say.
Okay, thank you. Goodbye, everybody.
Thank you. Bye.